So what do we fire our lasers at? Well, actually it's quite unglamorous sometimes. Sometimes it's just a little square of metal, but recently I've just had a target project with a company called SciTech Precision, and they've exquisitely manufactured some very, very small structures, because what I'm trying to do is when you fire a laser onto a piece of material and you've ionized that material, you can accelerate lots of very fast electrons, so mega amp current. And if you think about what that is, say lightning, that is sort of 30 kiloamps. So we've got this mega amp current being punched into a target. But what happens naturally, if you just shoot it at a square of metal, it sprays out and it diverges. These exquisitely engineered targets are designed so that there's a resistivity gradient, which means we can actually try and focus or collimate these electrons. And that's really useful for quite a number of different processes. So when we shoot lasers into different materials, it's because we're interested in the property of those materials. Certainly when it comes to plasma physics, something that's really important is the number of electrons available. So shooting a low Z target, Z being the atomic number, so therefore the number of electrons available, gives you different behaviour to shooting a much higher Z target. And also, sometimes it's just about what materials are available. So sometimes people will ask me, oh, why did you choose gold for that? And it's just because it's easier to machine than something else. So really, when we interact those lasers with the material, it becomes ionized very quickly. So actually what you're left with is not a bunch of atoms, but actually just some electrons swimming around with some ions. And so it kind of depends on what you want to do. For example, you can use a substrate material and then take a dopant, a little thin layer of something else, because you want to do some X-ray emission from that layer, and that tells you something about the amount of energy you put into that layer, for example. So you could have a sandwich of plastic with a little layer of copper in, and then some more plastic, and then you could do, for example, copper K alpha, which is when electrons come in and they can knock out a K shell electron, and then another electron will drop down and emit this characteristic line, and we can use that to diagnose what's going on. So it's kind of how long is a piece of string. There's a number of reasons why we'd use different materials, but sometimes it's just down to the practicality of what's available and what you can manipulate in target manufacture. The kind of targets that I'm interested in now are the kind of targets when we interact with a laser, we're trying to manipulate what the electron beam is doing. From a fundamental point of view, having control over that electron beams means you know where that energy is going. So it's not just spraying out everywhere, you can direct it somewhere. And once you can do that, then you can open up a whole world of parameter space to try and understand and study. So number one, you could use it as the spark plug for an alternative scheme of inertial confinement fusion called fast ignition. Currently, lasers like the National Ignition Facility over in the Bay Area are using a conventional form of ignition, whereby you compress a pellet with long pulse lasers converted into X-rays, and then it kind of self-ignites, so it's kind of like a diesel engine. Fast ignition is the kind of petrol engine approach to it. So basically it could open up a whole new method of producing fusion. Secondly, you can use it for more fundamental studies of high energy density physics. So I'm actually interested in hot dense matter. So if I can produce a large volume of hot dense matter, then I can use that to study interesting properties of material, like opacity, for example, which is kind of how opaque a material is, and then things like we can study properties related to nuclear astrophysics, we can study exotic atomic physics as well. So not only does it have practical applications, it also will allow us to drill into the physics of hot dense matter a little bit more, which there's quite a lot of unresolved areas in that kind of area of study of matter.